Rational functions. In this lesson, we're going to talk about the definition of rational function and their domains, the rational function in lowest term, the vertical asymptote and horizontal asymptotes of the graphs of rational functions, and of course the graphs and their end behaviors. Now let's look at the definition of rational function. A rational function is a function of the form px over qx, where both p and q are polynomial functions and q is not the zero polynomial. Zero polynomial means the polynomial of degree 0, so that's just a number, a constant. So it cannot be a constant in the denominator to have a proper rational function. Now the domain of a rational function is very important. The domain is all real numbers except the solution of the denominator equal to 0. Now let's look at an example of a rational function. F of x is equal to x plus 2 over x squared minus 4 is an example of a rational function where the numerator polynomial is x plus 2, which is degrees 1, and the denominator polynomial is x squared minus 4, which is degrees 2, so it is not a zero polynomial. Or another example, g of x is 1 over x squared minus 4. This is also a rational function. The numerator polynomial is degree 0 and the denominator polynomial is degree 2, so it's not a zero polynomial in the bottom, in the denominator, so it's a rational function. Now let's look at the domain. So to find the domain, first we need to solve the denominator equal to 0. So if you solve x squared minus 4 equal to 0, we can do two ways. We can factor it or use the square root method. So if I use square root method, x squared equal to 4 gives you x equal to plus or minus square root of 4, which is 2. So the domain is all real numbers, all x, such that x is not equal to these two numbers. X is not equal to negative 2 or 2. And this function also has the same domain because they both have the same denominator. Now let's see what a rational function in lowest term means. If Rx is a rational function and P and Q have no common factors, so the numerator and the denominator, if they don't have common factors, then the rational function is in lowest term. Now if we get the example problem, we got f of x is equal to x plus 2 over x squared minus 4. So this rational function is not in lowest term because the denominator, the factor, we can factor denominator, which is x minus 2 times x plus 2. So this is not in a lowest term because x plus 2 is the factor to both numerator and denominator. In fact, we can rewrite this function f of x equal to this one as, when you cancel out x plus 2, as 1 over x minus 2 if x is not equal to, see, this is equal to 0 when x equal to negative 2, when x is not equal to negative 2. So this function is same as this function if x is not equal to 2. So still the domain of this function is all real numbers except negative 2 and 2. Now let's look at the other example we had. F of x equal to 1 over x squared minus 4. This rational function is in lowest term because there is no common factor to both numerator and a denominator other than 1, of course. Vertical asymptotes and x-intercepts. If rational function Rx is in lowest term, then we can talk about the vertical asymptotes and x-intercepts of the graphs of those rational functions. The graph of Rx will have vertical asymptotes at x values where the denominator or qx equal to 0, and the graph of Rx will have x-intercepts at x values where the p of x, the numerator, equal to 0, of course if those values are in the domain of f. Now if we take this example, f of x is equal to 1 over x squared minus 4. The graph will have two vertical asymptotes because the q of x, or the denominator, is going to be equal to 0 when x equal to plus or minus 2. Can you remember? They are not belongs to the domain. So there are going to be two vertical asymptotes, at one at -2 and other at 2. So one at -2, so this is at -2 and this is at 2. And also, what about x-intercepts? So the numerator is not going to be 0 at all, therefore no x-intercepts. So this graph will have two vertical asymptotes, one at -2 and the other one at 2, and there will be no x-intercepts. Now, what about this function? G of x is equal to x over x squared minus 4. Again, this rational function, denominator equal to 0 at -2 and 2. The graph of this function also has two vertical asymptotes at -2 and 2. What about x-intercepts? So the numerator is going to be 0 when x equal to 0. So this has x-intercept at 0, or x equal to 0 is a x-intercept. Now let's look at the horizontal asymptotes of the graph of a rational function. In general, rational function of px, we write an xn plus an minus 1 xn minus 1 plus a1x plus a of 0, and q of x we normally write bn xn b n minus 1 xn minus 1 plus b1 x1 plus b of 0. Now if the degree of p is greater than degree of q, for example, your rational function is say x to the third minus 5x squared plus 8x plus 1 over x squared minus 1. So the degree of px, degree of p here is 3, the x to the power of the leading term, which is 3, and the degree of q in this one is 2. So if the degree of p is greater than degree of q, it's not a proper rational function. So this will not have no horizontal asymptotes. Now if the degree of p is equal to degree of q, an example, 3x squared minus 12 over x squared plus 2x minus 3. We can see the degree of p is 2 and the degree of q also 2, and then the horizontal y equal to an over bn, the leading coefficient, over the leading coefficient is going to be horizontal asymptote. So the leading coefficient of this one is 3. The leading coefficient denominator is actually 1. X squared means 1x squared. So this has, if I graph this one, we'll get the horizontal asymptote y equal to 3 is going to be a horizontal asymptote. Now, if the degree of p is less than degree of the q, example, say g of x, what we had earlier, 1 over x squared minus 4. The degree of the p is 0 and degree of the q is 2. So when the degree of p is less than degree of q, y equal to 0, the horizontal asymptote.